Our second speaker is Salammbo Connolly, and she will speak about continuation maps for the Morse fundamental group.
Yeah, thank you for the invitation. So yeah, I'm going to tell you how continuation maps work for the Morse fundamental group. So and now it works. The Morse fundamental group is if you have a Morse-Smale pair on a manifold M, you get a lot of topological information. And for the interest of this talk, you get in particular a very nice, in my opinion, combinatorial description of the fundamental group of M, which is generated by something we call Morse loops, which is if you take the unstable manifold of an index 1 critical point, so it's going to be a one-dimensional disk, which goes from one minimum to another one. And then you can orient it, so you go from one way to another, and you can form loops by concatenating them. And then if you want to take a set of loops based on a specific point, you can either take one of the minimums or take a generic point on your manifold and have a unique half trajectory that goes to a minimum. And if you conjugate by that, you get a set of loops that are based on that point. And then you can do the usual word reduction, which is that if you have two unstable manifolds, which are the same one with opposite directions next to each other, you can just cancel them out. And that gives you a natural group structure on this group, on this set. And then if you want to have a sense of the relation, so what it means for a Morse loop to be fillable, essentially what you look at is the unstable manifold of index 2 critical points, which are going to be two-dimensional disks, of which the boundary is actually a Morse loop. And so you can quotient by the normal subgroup induced by the boundaries generated by the boundaries of these unstable manifolds. And then you get what we call the Morse fundamental group. So for example, on the torus, you have two index 1 critical points, and the loops, each one has the unstable manifolds are actually loops in M, and so those are going to be the generators. And if you look at the unstable manifold of this maximum here, which is in the middle here of the flat torus, you go around the boundary, you get alpha here, then beta here, alpha -1, beta -1. And that's going to tell you that if you quotient by, so you say this is equal to 1, essentially the group is commutative. And so you get the usual fundamental group of the torus. And this holds in general. So if you have a Morse-Smale function, a manifold M, then the Morse fundamental group is isomorphic to the usual fundamental group of the manifold. So that can give you, for example, a lower bound in the amount of critical points of index 1 that you need, which in some cases can be better than the lower bound that you get from homology. And so there are several ways to see this. And one way is if you have a Morse-Smale pair, you get actually just a Morse function in general, you get a CW decomposition of your manifold. And then if you want to look at the fundamental group, you just need to look at the lower dimension, the lowest, the 0, 1, and 2 skeleta, and you can compute the fundamental group from that. But what's interesting is that in Floer theory, can be seen as an infinite dimensional generalization of Morse theory, but in general, you don't get CW decomposition of your symplectic manifold. And yet Barraud proved in 2018, I believe, that if you have generic choices of a Hamiltonian almost complex structure, you can actually use them to build the fundamental group of your manifold, which is going to be generated by, instead of looking at unstable manifolds of index 1 critical points, you're going to look at these dimension 1 moduli spaces of holomorphic curves with one puncture. And these are going to break like this in these broken curves where the top is a cylinder. And you can use that to concatenate them together and form Floer loops. And it turns out that the set of such Floer loops is going to be surjective onto the fundamental group of your manifold. And then if you want relations, it's a bit more complicated because you don't naturally have two-dimensional disks that are the unstable manifolds or the equivalent of unstable manifolds of two-dimensional two index 2 critical points. But what you can do is what Jean-François Barraud did is that he built relations by looking at broken trajectories in the boundary of components of dimension 2 moduli spaces, and he used that to build relations that give you an isomorphism. And if you want to expand this construction and get more applications or do it in other settings, be useful to have continuation maps, which in Floer theory typically are used to like see what happens when you smoothly deform the data. And they're used to prove invariance, but also to show symplectic to define symplectic cohomology or prove continuity of spectral invariance. And they typically done by counting rigid trajectories, but in the fundamental group setting, it's a bit more complicated because you're more looking at the actual topology of the moduli spaces. And so if you want to define such an object, a good place to start is understanding what happens in Morse theory. So typically in Morse theory, the continuation maps are defined by looking at functions. So if you have two sets of Morse-Smale pairs, you take a function in m times r, which before 0 is going to be equal to 1, and then after 1 is going to be equal to f2. And then you can, from that, build, by, for example, adding h, you can build a function that's on n times r such that the only critical points are going to be critical points of f1 at s is equal to 0 or of f2 at s is equal to 1, and which is decreasing between the two, so that then the flow lines go down from f1 to f2. And in particular, this shifts the index of critical points of f1 by 1. And then in homology, you define the morphism by just counting trajectories, rigid trajectories that go from the top of the hill to the bottom. And since if you look at critical points that are 2 apart, you get a one-dimensional moduli space that counting the elements of the boundary is going to tell you that this is a chain map. And we call this a continuation map. For the fundamental group construction, it's a bit different. You have to, so the loops are formed out of more steps, so one-dimensional unstable manifolds. And so if you have an index 1 critical point, it's going to become an index 2 critical point of big F. And so if you look at then the moduli space of trajectories, which go from this point and it's 0, are at a point in m times 0, 1, so somewhere between the top of the hill and the bottom, you get this half disk. And this side of the half disk is going to be the unstable manifolds of your critical points. And over here, you actually get a concatenation of more steps. And so you can use this to define a map, which to the step over here, which say goes from y2 to y1, you assign the concatenation of steps that goes from m2 to m1. And this map is actually going to be compatible with concatenation, because if you take like another step which ends in y2 over here, then you can see that the top of the half disk is actually going to be the same as this line here. And so then the concatenation of steps is also going to end in m2. And so then that tells you that you have a well-defined map on the set of loops of group morphism. And in order to show that it's actually a morphism on fundamental groups, you can't just count trajectories. You have to figure out what happens if you have a loop, which is the boundary of the unstable manifold of a critical point z of index 2. Then you want the image of such a point to be in the normal subgroup generated by unstable manifolds of index 2 critical points of f2. So in general, you can't hope that it's going to be just like the boundary of one critical point, but essentially the idea to have is that if here it's filled by an index 2 critical point, over here it's going to be all the holes are going to be filled by unstable manifolds of index 2 critical points or gluings of them. And so to show this, what you have to do is, so you have your index 2 critical point z, which then becomes an index 3 critical point of big F. And you have to look at, what we did was we looked at the moduli space of trajectories that go from this point and end or in 0 or in m times 0, 1. And the boundary, part of the boundary is going to be broken trajectories that break at s is equal to 1. And so you have to show that the trajectories of f2 which appear in that part of the boundary essentially form a space that looks like this image. And then you have to be sure that the image of each step appears in the right order along this boundary. So you have to analyze the moduli space and what happens quite carefully, but then it turns out that it works, and so you get a well-defined morphism on fundamental groups. And not only that, but if you then have 3 sets of such data, it turns out that they commute together in the sense that going from F1 to F3 is actually the same thing as going from F1 to F2 or from F2 to F3, modulo this change of base point. So you can't be sure that, in fact, in general, there's no reason why the base point would be the same, but it doesn't matter because essentially there's going to be this isomorphism, which is just going to be the conjugation with like a series of more steps, which go from one minimum to another. So to show this is kind of a similar thing to what people do in homology, which is that you look at, so you do a continuation map, a similar construction to the continuation function, except on n times the square rather than n times r. And so you wanted to, at the bottom, match F1 and on this side to match F1 tree. So that if you look at broken trajectories around here, you get the identity here and phi1 tree. And over here, you get phi1 2 and phi2 tree. And so what you want is that going around one side gives you the same loops on the other side, or at least the same equivalence class of loops that go on the other side. So in order to do this, what we did was you can, if you project the trajectories onto the square, you can see what angle they start. They go at in the square at the beginning, and you have to understand what happens when the angle goes from 0 to pi over 2, essentially. And what's going to happen is that for generic values of lambda, the restriction actually to this angle is going to be Morse-Smale, and so you can define a morphism from the Morse fundamental group of F1 to the Morse fundamental group of F3 in a similar way, in the same way as before, actually. And that the image of that morphism as lambda goes from 0 to pi over 2 is just going to change when you cross non-generic values. And so several things can happen. One thing that can happen is that as you go from 0 to pi over 2, there's an angle lambda at which so your critical point, your trajectory from the critical point x0, 0 at the bottom of the square is going to hit an index 2 critical points at the top of the square. And so what happens here is that before this angle lambda, your trajectory, your steps that appear in the image are going to go around one side of the unstable manifold of this point, this index 2 critical points. And then at lambda plus epsilon, you're going to end up just going around the other side. And so this is not going to be the same loop, but it's going to be in the same equivalence class. And something else that can happen is that at a point in the minimum which is going to be at the boundary of your unstable manifold of your index 1 critical point of F1, trajectory from that is going to hit an index 1 critical point at the top of this of the square. And so when this happens, essentially you lose a step in the image of your Morse step. But that actually doesn't matter because the whole thing is a loop, there's a periodicity. So if you lose a step here, the step is actually going to be gained in the loop that appears before in the Morse loop, in the image of the step that appears before in the Morse loop. And so in the end, you're still gonna get the same loop essentially, but the only difference is that it's going to account for the change in base point that appears in the commutative diagram. And so in the end, we can understand that all the changes that can happen, and in the end, in every case, you get a loop that is going to be equivalent to the loop that we had at pi equals 0, lambda equals 0 when lambda is equal to pi over 2. And so therefore, you get a commutative diagram, and that in particular gives you Morse proof that the Morse fundamental group is not dependent on choices. And that's most of what I wanted to talk about. And just the last thing I wanted to say was that I explained everything in the context of if you look at Morse-Smale data on one manifold M, but if you actually have a smooth map between two manifolds, you can look at grafted trajectories, which is trajectories that follow the gradient flow up until a certain point. And then at that point, you take the image at that point by H, and then you follow the gradient flow of the function on M and N by that from that point. And then those are grafted trajectories, and using those, you can define morphisms in the same way as what I described, which fits into a similar commutative diagram. And that's all I wanted to say. Thank you for your attention.
Thank you very much, Salammbo. So who wants to ask the first question?
Can I ask a question?
Please.
Hi, Salammbo. I have a question. So you have like these very nice theorems that people love to prove for homologies. For example, that there is something like Meyer-Vietoris, and for fundamental group that's Van-Kampen, right? So is it now possible if I have some like do you know how you could prove Van-Kampen with this? Like maybe even for other Floer theories?
Yeah, I think so. I did think about this a bit, and I think it should. Van Kampen should work kind of similarly too, just by replacing the proof of Van Kampen in the normal proof of Van Kampen with the analogs of that are going to be like Morse loops and stuff like that. Like it shouldn't be too hard to prove, and that should work. And then it should also work for the Floer fundamental group, I believe. But I didn't see the details.
Okay, thanks.
Can I ask a question?
Please.
So is there a possible analog of this for the Floer fundamental group, defining continuation maps for that?
Yes, I'm looking at I'm like thinking about this at the moment. That was the motivation at first. It's slightly harder because you have less control over what the moduli spaces look like. In Morse theory, everything's a disk, and so things work very well. And in Floer theory, it's unclear how you have to maybe have a bit harder algebra if you want it to work, so that you understand more what the image of the steps is going to be. Because, for example, in the Morse case, you have a step over here, and then you have a half disk, and so the boundary over here is going to be a connected series of steps. But in the Floer case, it's even though we know how to by Barraud's construction, there's methods to produce a disk all the same, a connected disk all the same. It's not clear that the other side is going to be connected, and so therefore you don't know what the image of each step is going to be. Maybe we have to define things a bit differently. I'm like thinking about it at the moment.
Okay, thanks.
Octave.
Yep. So maybe hi Salammbo. So maybe related a bit to this question of Michael, there are some proofs of invariance for various things like Morse theoretic complexes or Floer theoretic that involve action control. And so these were not necessary at the beginning. I mean, when you just do Morse theory and maybe even for Floer theory, somehow the control for action can be not very significant. But maybe that's some way to try to see if using action control, you first can prove Morse a little bit maybe more efficiently than what you have now, and then maybe to try to push that over to Floer, to the Floer fundamental group. I don't know, it's just like a comment more than a question, I guess. But
I think I hadn't thought of that actually, but that maybe could work and maybe could simplify.
Because the basic idea is when you do this. So initially, Floer, when he proved invariance, there were two methods. One was like bifurcation method, which was very complicated because it was bifurcation method for Floer theory. And then the other one was this sort of continuation map method, which was based on doing Floer theory with one dimension more. And the bifurcation method, in fact, has kind of an action-based control system that I think maybe, I don't know, I think I saw something like this. Some people of Abu Zaid and Krag at some point. But in any case, that kind of does something a bit better than what we used to. I mean, you need less control understanding explicitly the perturbations using that. That's the main point.
Okay, yeah, that's really interesting. I'll look into that. Thank you.
Other questions? Okay, so sorry, I'm totally ignorant about this topic. So the Floer fundamental group, is it defined or not?
Yes.
Right.
And it's isomorphic to the usual fundamental group of the manifold, but the difference is the relations are a bit complicated, and so maybe continuation maps could improve. You could then get a continuation map with a small Hamiltonian, and then that could improve. You wouldn't have to get such complicated relations to define the invariance.
Maybe you should say that it was defined, this Floer fundamental group, by Barraud.
Yes,
Right.
yes. I think I said it in my
Yeah, sorry,
But it was Jean-François Barraud did it, and he's done several papers in various settings of this.
So how is this pi1 for Floer theory related to Floer homology? Is it by so it should be abelian pi1 of Floer, no? Because it's on the loop space and it's an H space, and pi1 of an H space is abelian. Is it not true?
I mean, so yes, it is because of the fact that that is isomorphic to the fundamental group of the manifold, and so therefore the homology, symplectic Hamiltonians or homology is also isomorphic to the homology.
No, I don't think it's abelian. And in fact,
I mean,
right.
I understood that it was an abelian, like the homology is an abelianization.
Yes, you see, it's not the fundamental group of the loop space.
I see, that's wrong.
It's a fundamental group. It mimics the fundamental group of the space itself.
Yeah.
I see.
Sorry, I misunderstood your question.
Yeah, like in classical Floer. Okay. So usually pi1 by abelianization goes to H1. So what is it here now? Is it a certain one has to
we
grade?
have that explicit map from pi1 to H1 without going through the isomorphism with the normal topological fundamental group and homology. But that would be interesting to have.
Okay, thank you.
Yeah.
Other completely uninformed questions?
Is there analog in Lagrangian Floer theory?
Yeah, I think it hasn't been, to my knowledge, hasn't been written. But I think it should work in the same way as I think Jean-François Barraud sorted out a lot of the details for that, but it should work very similarly.
But okay, so now if you do pi1, you can also do pi k. So do you get to Floer homotopy theory? Is it directly related or not? Or
well, Floer homotopy theory, as far as I know, is mostly stable groups, and so I think the trouble is even in the Morse homotopy groups, it would be very difficult to have actually explicit computations used, because you can always, like, if you have a CW complex and you look at the skeleton up to that point, compute the homotopy groups up to that point. But then, for example, if you want if you want higher homotopy groups, they behave strangely, and so like you don't know how you need to you need to look at the unstable manifolds and how they glue together. And then, for example, pi 3 of S2 is not trivial, and so then that could you would actually get a lot more complicated phenomena. Whereas if you look at just pi1, it's just going to be loops formed by one-dimensional disks, and so you're like one-dimensional lines, and so you understand how they glue together, and you can understand a lot of what happens. But I think it's more complicated if you want higher homological groups.
Thank you.
I have a question. Did somebody do this Floer fundamental group for the symplectic cohomology? And you get the fundamental group of the free loop space, like a Viterbo isomorphism?
No, but because you would need continuation maps for that. So since the continuation maps haven't been done.
The continuation maps are not done to take the direct limit, you're saying?
Yeah.
In symplectic cohomology.
Yeah. But anyway, yeah, it would be unclear, because I guess in the end you would get then something abelian that would be isomorphic to the homology, the loop space. So, but maybe it wouldn't be perfect too. I don't know. But that would be interesting to look into.
That actually would be really nice if you can do. Oh, sorry, if you could do that kind of thing, you would have the pi1 of the loop space, which is just pi2. And so you could do, if in theory you could do that, then you could already have like a Floer pi2, which would be really nice.
Well, it's free loop space. I don't know if that complicates it, but
I don't know. I mean, I guess, yeah, because the free loop space is just going to be, that's what Polio said, is that like pi1 free loop space, just like pi2 of the underlying space. And so.
Well, that's base loop space, right? But anyways, I digress. I'm being a little bit anal about that, but sorry.
Yeah, maybe you're right.
That's interesting.
So about that question, so I think that when you define a symplectic homology, you can choose the Hamiltonian quadratic at infinity, so you don't need a contribution map. So can we do that in that way? I'm not sure if it's known.
I didn't. If my Wi-Fi kind of went for a second.
When you define a symplectic cohomology, you don't really need contribution map. You can choose a quadratic Hamiltonian at infinity. But instead, you need some maximal principle.
Yeah, so, that case, interesting. And then, in that case, you could see what that, to my knowledge, has not been done. But then, in that case, you could see if the Viterbo isomorphism holds for fundamental groups, for example.
Oh, okay.
But thank you. I didn't know that about symplectic homology.
Okay, in any case, thank you very much again for this very interesting talk.